So the next topic that we are going to discuss is dielectric polarization. Polarization is a topic that would be discussed twice in field theory. First time we would discuss here in this topic, that is dielectric polarization, and again we will visit this polarization concept in electromagnetic wave chapter. What do you understand when I say dielectric polarization? When do you say a dielectric is polarized? What is a dielectric? Dielectric is an insulator, and you know the difference between an insulator and a conductor, right? An insulator is a material which has bounded charges. Insulator is a material which does not contain any free charges. Conductor is that material which contains free charges. So the impedance of a conductor is very less when compared to the impedance offered by a insulator. So when do you say that a dielectric is polarized? A dielectric is said to be polarized when it is placed in a strong electric field. When high electric field, not even moderate electric field, when very high electric field is applied onto an insulator, is applied onto a dielectric, then we say that the dielectric is polarized. So if you look at the basic theory behind polarization, there are two types of molecules that are usually considered. One is polar type dielectric molecules, and the other one is non-polar type dielectric molecules. One is polar type, the other is non-polar type. The basic difference between polar type and non-polar type dielectric molecules is the center of positive or negative charges. For the case of polar type, they are permanently displaced. There is a permanent displacement between the centers of positive and negative charges for the case of polar type dielectric molecules. For non-polar type dielectric molecules, the centers of positive and negative charges they coincide. That means there is no displacement of the centers of positive and negative charges for this type. Don't think that this displacement is because of the electric field applied onto it. No, this is not because of the electric field applied onto it. Even when electric field is not applied, then also there is a displacement between them. That is why this is called polar type dielectric molecules. Now when electric field is applied onto either polar type dielectric molecules or non-polar type dielectric molecules, the centers of positive and negative charges they are slightly displaced. Like if you consider this case where there was no initial displacement between the centers of positive and negative charges, when strong electric field is applied onto this type of dielectric molecules, then the centers of positive and negative charges slightly displaced. So positive charges move along the field and negative charges move away from the field. Say these charges are Q, and if the displacement between the charges is D, we also talk about the dipole moment small p, that can be found out as the product of the charge and the displacement between the molecules. The similar phenomenon would occur for polar type dielectric molecules. However, when you don't apply this electric field, they come back to their original position. That means they come back to a position where the displacement is x dash for polar type, and for non-polar type there is no displacement between the charges. So it has been found out that analysis with polar type dielectric molecules is pretty complex because of its inherent nature of having a permanent displacement between these positive and negative charges, while non-polar type is relatively easy to analyze. So that's the reason every time when we talk about dielectric polarization, So we will consider only non-polar type dielectric molecules. We will not consider polar type dielectric molecules. But it is better you understand that there is two types of dielectric molecules, both polar type and non-polar type. Okay. Now this polarization again is a big topic in itself. We will take this as a separate topic at a later stage. But now when we say dielectric polarization, so what happens when the dielectric is polarized? That means what happens when strong electric field is applied onto a dielectric? What are those quantities that get affected because of this polarization? So in short, when strong electric field is applied onto a dielectric, then the electric flux density d bar will not have the same value as it had in free space. What was the value of d bar in free space? D bar will have value epsilon naught E bar. So in free space d bar is equal to epsilon naught E bar. When strong electric field is applied onto this dielectric, the electric flux density will not have the same value as it had in free space, but it will have value greater than the value it had in free space. And what is that value? That is P bar. D bar will be equal to epsilon naught E bar plus P bar, and P bar is referred to as polarization vector. And P bar can be found out as P bar is equal to epsilon naught chi e into E bar, where chi e is called electrical susceptibility of the medium. This is called electrical susceptibility of the medium. So if you substitute P bar as epsilon naught chi e into E, then you get D bar as epsilon naught E bar plus epsilon naught chi e into E bar, or this will be equal to 1 plus chi e into epsilon naught into E bar. This 1 plus chi e can be represented as epsilon r, that is the relative permittivity of the medium. So you get D bar as epsilon into E bar. So I don't want you to understand the relation between D bar and E bar as D is equal to epsilon E, because we already know the relation between D and D as D is equal to epsilon E. What I wanted you to understand is the relation between the relative permittivity and the electrical susceptibility of the medium. Epsilon r is equal to 1 plus chi e is a relation between them. Very important. You can expect a simple 1 mark question or sometimes even a 2 marks question on this. In the examination, he will give you the susceptibility as say 2.4 or 2.8, and then he'll ask you to find out either electric field intensity or electric flux density or any other quantities that are related to these types. So you should be aware of this relationship. Similarly, we will see one more relationship in magnetostatics, that is a relation between mu r and chi m, that is relative permeability to the magnetic susceptibility of the medium. That will be mu r is equal to 1 plus chi m. Very important. Okay, so you can expect a question on finding out the magnitude of polarization vector, or finding the polarization vector itself, or given chi e, he may ask you to find out epsilon r, or given chi e, he may ask you to find out D bar or P bar. So take some tests in www.10pointer.com and you will find few questions asked on this topic as well, and you would see how questions can be asked or how questions are asked in the examination. Now let us move to the next topic. that is equipotential surface. When do you say a surface is equipotential surface? Or what do you understand when I say equipotential surface? On this surface, the potential is equal at each and every point, and also it is constant. So it is a surface on which potential is constant and equal at each and every point. Each and every point. Right? That is what we understand by the name equipotential. Or can I say that it is a surface on which the potential difference PD between 2 points is 0? Between 2 points is 0? Because when potential is equal and constant, then the potential difference between the 2 points will be equal to 0. Or it is a surface on which the work done in moving a charge from one point to another point is equal to 0. Because we know work done is related to the potential difference between 2 points. It can be VAB or VBA. So if the potential difference itself is 0, then the work done in moving a charge from one point to another point is equal to 0. So all these 3 points are related to the equipotential surface. So when you say equipotential surface, the potential is constant and equal at each and every point, or the potential difference between 2 points is equal to 0, or work done in moving a charge from one point to another point is equal to 0. Now these 3 are related to each other and just straightforward and easy to understand. Now we need to understand one more property which is quite significant, which is unique only for equipotential surfaces. What is that? Let us consider a closed surface S surrounded by electric charge Q. We know the moment we say electric charge Q, there are some lines of flux emerging from this surface, and they are trying to terminate on a negative charge, right? So the field is interpreted in terms of several lines of flux emerging from the surface, right? And you could consider them as electric flux density lines or displacement density lines or electric field intensity lines also, because I told you when we don't talk about the kind of material we are considering, it will be an isotropic material, and we know the relation between D and E for isotropic material. D is equal to epsilon E. Epsilon is constant, so it is like A bar is equal to K into B bar. So one vector is a scalar multiple of the other. That means they are parallel to each other. So I can call this as D bar direction or E bar direction. Both of them mean one and the same. Now this vector can be split into 2 components. This is electric field vector, right? This can be split in 2 components. This is one component, and then this is the other component. Right? This component is called E tangential, and this would be E normal. So electric field vector typically can be split into E tangential and E normal. So E bar